Welcome back to another session for thermodynamics subject. In this session, we are going to discuss about the energy analysis for the control volume, different type of open system actually. In previous session for this chapter, I have introduced you a steady flow, and I have introduced you some steady flow devices as well. And we have seen different examples how we can calculate the energy balance, how we can find the different properties for uh, those devices. Here in this session, I'm going to start to discuss about the energy analysis for unsteady flow process. However, in many of the industrial equipment or devices, we have a steady flow, but there is also situation or equipment or devices which we have also an unsteady flow process. How we can write energy balance equation for these devices, or how we can select the control volume for these devices. As we have seen in a steady flow process actually, usually the bound we have a fixed boundary for a steady flow process, but here we generally, in most of cases, we have a variable boundary for control volume, and also the that in for energy balance we have a change in the energy of the control volume. We have change in the uh, mass of the control volume as so. As I discussed, many process of stress involve changes within the control volume with time. We call them unsteady flow process called or transient flow process. Actually. Then what but we can have some assumption to simplify the calculation for these systems as well. The first assumption is for many of these unsteady flow processes, we can represent reasonably the flow in this process as a uniform flow process. What is uniform flow process? Uniform flow process is the flow of a fluid, which in that flow, any inlet or exit of the control volume is uniform and steady. In other words, in a steady flow, we had a steady flow in whole system, and we don't have any change of the flow in entire control volume actually. But here in this type of unsteady flow, which we call them uniform flow process, the in the cross section, in the imagine like what we have here at the entrance of the or at the exit of the control volume, we have a uniform flow or a steady flow actually. And it means the properties of fluid at that cross section do not change with time or a position over the cross section of an inlet or exit. So, uh, however, the properties of the flow changes with time, but we can assume that we have a uniform flow, which it means at the exit or at the entrance of the control volume for just the cross section, the properties of the substance is constant and it does not change with time only for that cross section, not for whole control volume. And if it is changing, actually, we need to assume that to find an average for that cross section, and we can assume that we have a uniform flow for that cross section. This assumption will help us to solve this kind of uh, solve different kind of problem for these unsteady flow processes as well. Some examples of this kind of process are like this, which is charging of rigid tank from a supply line. This is a common device actually or process in industry. We have a supply line and a tank. We are going to fill this tank by this supply line, which is very common type of the devices or equipment in the industry. Then, as you notice here, if we select the tank as our control volume, or we select the gas inside the tank as our control volume, we in with if with each one of these control volume, actually the flow rate or the flow which is coming to the control volume is changing with time, and discharging it is unsteady flow process since it involves changing within the control volume. The other example is the what you can see here. Here we have rigid tank. We may have a piston cylinder device. Then the gas is the fluid is coming to this cylinder piston, and we have a boundary work of this control volume. Here we don't have any work, but here we have work as a boundary work of our boundary. Here it is the we have a control volume because mass is crossing the boundary of our control volume, and this is an unsteady flow process because the flow is actually unsteady. The uh, flow rate to the control volume is changing with time. Uh, if it is constant flow rate, we have a steady flow. But if it is not, if it is changed with time, we have unsteady flow process. And you can see here one with boundary work, one without boundary work. Then if we write the mass balance equation and energy balance equation for such a unsteady flow process, actually, in this case, if you write mass balance, ME, which is the mass come to the system or control volume, minus M out of the system, which is the mass going out from the control volume, give us will be delta M of the system. Delta M of the system here is not zero. Why? Because we have an unsteady flow. Then delta M of system actually will be the final mass of the control volume minus initial mass of the control volume. Imagine we select the gas or the fluid inside this tank as our control volume. The initial volume is zero because we don't have any gas inside the control volume. Then the final state, we assume the tank is filled completely by the fluid. Then the final volume or mass is the M final, which is the whole mass of the gas inside the control volume actually. So delta M of the system is M final minus M initial. We have seen this equation in previous slides as well. If we so then this is M in minus M out by this equation actually is equal to M final minus M initial. If we rewrite it like this, instead of M in, we write Mi, or inlet actually, inlet mass to the system, or control volume minus Me, which is the exit mass from the control volume, is equal to, instead of M final and M initial, we can show by 2 and 1. Then We can write M2 as M final minus M1 as initial mass of control volume. So the mass balance which we can write for an unsteady flow process is like this: Mi minus Me equal to M2 minus M1 of control volume. And if we write energy balance equation for an unsteady flow process, as usual, E in minus E out equal to delta E of the system. E in minus E out means net energy transfer by heat, work, or mass to of the control volume, and delta E of the system is change in the internal energy, kinetic energy, potential energy, or other type of the energies of the system. What are the E into the system? E into a control volume is equal to the heat which is transferred to the control volume or thermal energy, work which is done on the system or W in, plus summation of M theta which is introduced in previous sessions, which is total energy of the flow which is coming to the control volume times the mass uh, of the flow which come to the control volume. This one, which if we just expand it, it means it should be like the theta is equal to H enthalpy plus kinetic energy plus potential energy. These terms summation of or sigma in m theta actually is mh plus mke plus mpe, or because or in terms of rate, if we can write like this, if we have this, and the energy which go out from the system is heat transfer from this control volume Q out, work which is done by the system or control volume W out, and sigma out and theta. Same here, but this time which is related to the flow which going out from the system. So this is E dot in, this is E dot out for an unsteady control volume. And delta E of the system, M2, E2 minus M1, E1 for system, which E is equal to U plus KE plus PE, which E is total energy of the system actually, and U is internal, which is equal to microscopic and macroscopic energy, or U plus KE plus or kinetic energy and potential energy actually. So M2, E2 minus M1, E1, which E2 means U2 plus KE2 plus PE2, or internal energy at the final state, kinetic energy at final state KE2, potential energy PE2, potential energy at final state, and U1 KE1 uh, internal energy, kinetic energy, potential energy of the system at the initial state. Actually, so this is the general equation for our control volume. We can write this equation like this: Q minus W, which Q is Q net in of the system, which is equal to Q in minus Q out. We had this equation: Q minus W equal to delta U. If you remember, we had this equation for a closed system. For a control volume, it is changed to this because we have this term mh uh, uh, mass of the uh, flow times the mass of the control volume actually, times its enthalpy. We have this because here we have a flow. Energy also is transferred to the system or transfer from the system by mass as well. So we add these terms. This is difference between this equation which we had for a closed system with the equation which we have for a control volume. Q minus W equal to summation of mH for out the flow which go out of the system minus summation of mH mass times enthalpy of the flow which going out of the system plus m2 u2 minus m1 u1, which m2 and m1 are the uh, initial mass and final mass of the control volume. U2 and u1 are the final internal energy and initial internal energy of the system. And Q, as I said, is equal to Q in minus Q out for the control volume or system. W is equal to W net out for control volume, which is equal to W out minus W in. If you remember, this is sign convention which we had for closed system as well. Here, just this term is added for to the control for the open system or control volume which we have here. And for a open system for control volume, if we close all of the flow, if we restrict the flow and we have Q and W interaction between the system and surrounding, then this equation will be converted to this equation which we had earlier, which is Q minus W equal to M2U2 minus M1U1. You can see the closed system is actually a simplified form of the more general equation which we have for a control volume. And this is due to this fact that for a closed system we don't have any mass transfer to the system. And you need to notice also for control volume, especially for unsteady control volume, we may have different types of works like boundary works, electrical work, or shaft work. So for a uniform flow system, we have electrical, shaft, boundary work all at once together for a control volume. In few example, next slide, we will see how we can use this information to find different properties for unsteady flow uh, by selection of appropriate control volume and using these equations. Here we have an example which is related to this unsteady flow process. As I said, one type of this unsteady process, unsteady flow process, is charging of a rigid tank by a steam. Here we have a rigid tank which is connected to the charging line actually. A steam is flowing to this charging line. If we open this valve, a steam will come to this rigid tank. And the flow rate of the gas, flow rate of this steam to this tank is dependent on the properties of the steam and also the temperature and the volume which can come to this tank is dependent on the uh, properties of the steam. So we have a rigid insulated tank. So we don't have any heat transfer for this tank because it is insulated and it is rigid. So its volume also doesn't change. Initially, it is evacuated, so we don't have anything inside this tank before flowing off the flow from this line to the tank. Then this tank is connected to this stream. The valve is open, and the steam, which its pressure is 1 megapascal, and its temperature is 300 degrees Celsius, will flow to this rigid tank. Uh, and this process will continue until the pressure of the steam inside the tank also reach uh, 1 megapascal. And after that, actually, because the pressure inside the tank is equal to the pressure of the stream, we don't have any charge or any mass transfer from this line to the tank generally. Or it is mentioned that we open the valve, we give enough time to this stream and tank until the pressure inside the tank reach 1 megapascal. Then we close the valve. What we need to determine is actually we need to determine the final temperature of the steam inside the tank. So we don't know how much is the temperature of the steam inside the tank. Temperature is 300 degrees Celsius. Temperature inside the tank, we don't know how much it is. Then how we can calculate it? First of all, here what this process is according to the control volume which we can select, we can guess that it is uh, we need to select the control volume here, an open system. Why? Because we have a mass transfer to the tank, and moreover here the process will be an unsteady flow process. Why? Because uh, mm, as we can guess, initially the uh, mass flow rate to the tank, rigid tank, is higher when it is more uh, when we have more mass of the steam inside the tank, the mass flow rate will reduce. And also, it is not mentioned anything about the flow. So, with common sense, we can guess that we have an unsteady flow process. So, but we can analyze this process as uniform flow process. Why? Because properties of steam entering the control volume remain constant during the entire process. In other words, here the entrance of the control volume, if we select this as our control volume, this dashed line, steam is going to the tank through this valve actually. And if we select this as entrance of our control volume, the pressure and temperature of the entrance of our control volume will be always equal to pressure and temperature of the stream during the whole process. So during the whole process, we have a uniform flow uh, to the control volume. Uniform flow means the property will be constant, doesn't change with time. The pressure will be 1 megapascal and temperature will be 300 degrees Celsius during this charging of tank process actually. And assumption number 2 is the kinetic and potential energy of the stream are negligible and we can ignore them. The tank is stationary and thus its kinetic and potential energy of changes are also zero. Delta K equal to delta P equal to 0. Then changes in the energy of this system or our control volume is only due to the change in the internal energy of the control volume or the system. And also there is not any type of the work like boundary or electrical or shaft work interaction in this process. And the last assumption is the tank is well insulated, then we don't have any heat transfer for the tank, which is going to be our control value. Then we select the tank. We take the tank as our system, And if you notice here, as I discussed earlier, we have mass transfer through the boundary of our system, so we have a control value. And as I discussed earlier, the process here is an unsteady flow process since changes occurred with the within the control value. Within the control value, the mass flow rate or the other properties actually are uh, changing. But we have this information as well. Its initial mass of the steam inside the tank is 0, and its initial uh, energy or internal energy also, because we don't have any steam inside our control volume, it is evacuated, nothing inside in the control volume. Then M1 U1 or internal energy of the system or control volume is 0 as well. So we have this information for initial state of the control volume. Then the microscopic energy of the flowing and non-flowing fluid are represented by enthalpy and internal energy. Enthalpy for the flowing uh, uh, fluids to the tank, and internal energy or U for non-flowing fluids, which we will have after a while inside the tank. And the mass energy balance for unsteady flow or for uniform flow as the unsteady flow can be written like this. For mass balance, we have this equation m in minus m out equal to delta m of the system. Familiar equation for you. We had these previous examples and also sessions. Then m in minus m out. M in actually, which this delta m of the system is m2 minus m1. We don't have any m out from the system, 0. Then we have only mi to the system. If you remember this equation, this is this equation actually. Then m in, we have m in coming, the mass which come to the system is equal to mi. We don't have m out, no mass transfer from the control volume to the surrounding, and delta m of the system is equal to m2 minus m1. As I discussed earlier, m1 is equal to 0, then mi will be equal to m2. In other words, the final amount, the final mass of the steam inside our control volume will be equal to the mass which is transferred from this steam or surrounding, from this line or surrounding to our control volume, or mi equal to m2. Then if we write energy balance equation for this control volume, E in minus E out equal to delta E of the system, the energy which come to the system is energy which come to system by uh, flowing fluid or flowing steam to the control volume, which is MIHI, and the we don't have any E out because we don't have any energy going out from our control volume, no heat transfer, it is insulated, no change in potential energy, no change in the, and for delta E of the system actually we don't have any uh, kinetic and potential energy changes, and also as m1 is equal to 0, then the change in the delta E of the system, if you remember this equation actually is this equation. We use this equation for our system here. Then here we have only MIHI as E in to the system. no heat transfer to the system, no work involved in the system, and E out also no heat transfer from the system or our control volume to the surrounding, no work output. So E out is 0 and E in is equal to MIHI. Only energy come to the system. Net energy transfer to the system is due to the energy transferred by the flow. And delta E of the system is M2U2 minus M1U1. As I discussed earlier, M1U1 is 0. Then we have only M2U2. And this is because we don't have any change in kinetic and potential energy. If we have them, we need to include them as well, as we discussed earlier. But we don't have them, then we can ignore them. So MIHI will be equal to M2U2. So we have the general equation. Combining the mass and energy balance by the mass balance, we found that we have Mi equal to M2. In other words, Mi and M2 here are identical. So we can cancel them and we can just write Hi equal to U2 or this. In other words, the final energy of the control volume or steam in the control volume actually is equal to initial enthalpy of the control volume, or the final internal energy of the steam in the tank is equal to enthalpy of the steam entering the tank. The enthalpy of the steam which is entering the tank is as equal to the enthalpy of the steam flowing inside this tube, which we know its pressure, we know its temperature, we know its pressure, and also we know its temperature. Pressure is 1 megapascal, temperature is 300 degrees Celsius. So by this information, we can go to table A6, which is for superheated actually, because we have a steam here, so we know that we have a steam, and if we compare the properties which we have here, we can understand also we have a superheated vapor of water. Then we can find Hi or enthalpy for water with these properties: 1 megapascal pressure and 300 degrees Celsius temperature, which if we go to table A6, we can find this by directly or by interpolation. H will be 3051.6 kilojoule per kilogram. So we found the enthalpy. But the question was we need to find temperature of final state. But as it is mentioned, and as we found earlier, this H we found in this step is equal to the internal energy or U2 of the system. Then it is mentioned that this process will continue until pressure inside the tank reaches 1 megapascal. Then we close the valve. So we know the final pressure inside the tank, or P2, which is 1 megapascal. And according to this equality, we know the final internal energy also is equal to 3051.6 kilojoule per kilogram. So we have the pressure, final pressure, uh, and we have internal energy of the tank at the final state. By this information, again, we can go to the table A6 especially. We can find temperature of water with this pressure and temperature in this table. We have pressure, we have its internal energy, then simply we can find temperature of the water or steam superheated vapor of water with these properties in this table. Then you can see how we can use those equations to find the final temperature of the gas inside this charged tank, which is attached to a uh, mm, line which contain a flow of the steam. Here we have an interesting, very interesting example actually for that unsteady flow process. And we have some notes in this example which are very interesting and will show you how you can use those information like which you have learned up to now to find the answer for this problem. In this question, we have an insulated 8-meter cube rigid tank. So it is we have a rigid tank. Its volume also is given. This rigid tank contains air, which is temperature is 600 kilopascal, and its temperature is 400 kilopascal. So P1 and V also is given, and also initial temperature. A valve connected to the tank is now opened. We have a tank, we have a valve, we open the valve, and air is allowed to escape until the pressure inside drops to 200 kilopascal. So P2 is 200 kilopascal after Y. Uh, the air temperature during the process is maintained constant by an electric resistant heater placed in the tank. In other words, if we open this valve, because we don't have any other mass through this tank, then because this air is escaping from the tank, its pressure will reduce and also its temperature will reduce. But we can keep its temperature constant by using up this electric heater or electric resistance actually. We need to determine how much electric energy is required or to supply to this air during this process to keep constant to keep the temperature of the air inside the tank constant. So how much is W into this uh, tank actually? First of all, let's see what should be our assumptions for uh, this example. This is an unsteady process. Why? Because the conditions within the device are changing during the process. As you can see also here, we have the mass is just going out from the cycle. We don't have a steady flow to the tank and going out from the tank. We have only one output for this tank. Generally, which when we have only one tank and we don't have a flow come into the system and going out from the system, we have an unsteady flow process generally. But we can assume that we can analyze this problem as a uniform flow process. Why? Because the exit conditions remain constant. In other words, this is the air is escaping from this. Then the condition at the exit will be constant. It may be atmospheric pressure and so on, or temperature, but generally we can say that it is constant condition. So we can say that we have a uniform flow process from the exit of our tank. Moreover, we can assume that kinetic and potential energy are negligible. The tank is insulated and therefore we don't have any heat transfer from the tank or to the tank from surroundings. And the air is an ideal gas. We can find that by comparing these properties with the critical properties of the air as well. Then we can have this assumption as well. There is an ideal gas with variable specific heats. Means the specific heat change with the temperature. Then we need to select our control volume. We select inside the tank as our control volume. Initially, whole the tank is filled with air, then it's the mass of air inside the tank will be different. So if we write the mass balance for our control volume, and if you notice our control, we have the system which we have selected, the boundary is open system. Why? Because the mass is crossing the boundary of our system. So we have control volume here, we have work to the system, we have the mass flow rate going out from the control volume. Then if we write mass balance equation for this, M in minus M out delta M of the system mass balance equation, we don't have any M in or mass come to the system, so M in is 0. What about M out? We have air is escaping from our control volume, so we have M out. We write as M in as we discussed earlier. And delta M of the system, as we discussed earlier in this equation, if you remember, delta Mi minus Me is equal to M2 minus M1. Here in our example, we have Me. Actually, this equation, if we write, will be like this: Me equal to M2 minus M1 multiplied by negative sign, then it will be like this: Me equal to M1 minus M2 by mass balance. Then if we write energy balance equation for our control volume, what are we have E in minus E out equal to delta E of the system. What are the energy coming energies which transfer to the system? The work, the energy, electric energy which come to the system by this heat, resistant or heater, WE in come to the system. We don't have any other type of energy come to the system, and so we have E in is equal to WE in only. What about the energy which going out the system? The energy which is leaving the system or from the system to surrounding actually is only energy which is transferred by the mass transfer, which is MEHE of the system actually. M is the mass of the air which is escaped from the tank, and H is enthalpy of that air which is escaping from the our control volume actually, equal to M2 U2 minus M1 U1. This is according to the equation which we have seen also in previous slides. We have only this is the change of the energy of the system, because we don't have any change in the energy of this in the kinetic energy of the system, any change in the potential energy of the system, and we don't have any heat transfer from the system. So the change in the energy of the system is only uh, due to the change in the internal energy of the system. So M2U2 minus M1U1. So we have also this equation. Then we need to solve this equation. Actually, we need to find M1, M2, Me, and so on for the air inside the tank. Me is the final is the amount of the mass of the air which is escaped from the tank. M2 is the final mass of air inside the tank, and M1 is the initial mass of the tank inside of the air inside our control volume. Let's see how we can find them. We can use this equation, which is the ideal gas relation. You have already seen that in previous chapter and slides. M1 equal to P1 V1 divided by R T1. P is the pressure at the state 1, V1 is the volume at the state 1, T1 is the temperature of the air at state 1, and R is the gas constant of air, which is equal to 0.287 kilopascal meter cube per kilogram Kelvin according to table A1, which is representing the ideal gas properties of different substances. One of those substances is air. So in this table, you can find R, or gas constant for air. By substitution, this in these properties which we have P1, we have V initial volume of the air is 8 meter, or our control volume, or which contain air, is 8 meter cubed, or we have an initial temperature also is given. Then we can calculate the M1, or initial mass of the air inside the tank. How about the final mass of the air inside the tank? With same equation, but this time pressure is reduced to 200 kilopascal, the final state. It was mentioned that initial pressure is 600 kilopascal. After we open the valve, the air is escaping until the pressure inside the tank reach 200 kilopascal. Then we close the valve. So the final pressure is 200 kilopascal. How about the volume? Volume, because we have selected our uh, control volume like this, the volume of the air, or our control volume, will be equal to its initial volume, which is 8 meter cubed. And the temperature also was mentioned that is will remain constant. So the final temperature also is 400 Kelvin by this equation. And these values for these variables, we can calculate the M2, or the final mass of the air inside the tank after closing the valve. So you can see here how much is the mass which escaped from the tank. We have the initial mass, we have final mass. So difference between these two masses will give us the uh, mass which is escaped from the mass of the air which is escaped from our control volume. Or ME is equal to M1 minus M2. M1, 41.81 kilogram. M2, or final air inside the tank, is 13.94 kilogram. So the total gas which uh, is escaped from this rigid tank during that discharging process is 27.87 kilogram. So we have all of this information, M1, M2, and ME, to be used in this equation. We have ME, we have M2, we have M1. Now we need to find HE, U2, and U1. To find these properties, we can go to the table, the enthalpy and internal energy of air during this process, this discharging process. The temperature is constant for 100 Kelvin. Then if we go to table A17, for this temperature, 400 Kelvin, for 400 Kelvin, we can find enthalpy. We can find enthalpy, the first column. We can find the internal energy as well. So HE we can find in the table, which is 400.98 for air in this temperature. H is this much, and U is 286.16. And because temperature of the air is constant during this process, then U1 is equal to U2, because U is dependent only on temperature for ideal gases. So if temperature is constant, it means U, or internal energy, is also constant. U1 equal to U2 equal to 286.16 kilojoule per kilogram. So we have HE, U1, U2. Then this is the equation which we have by restructuring, just transferring MEHE to the right side of the equation. We have this equation. WE in, or required electric energy, or work to keep the temperature of the air constant during this process, is equal to MEHE plus M2U2 minus M1U1. And we have all of these information, the values for all of these properties to calculate WEE. If we substitute the values which we found for all of each one of these properties, we can calculate WE in, which is equal to 3000 kilojoule or 0.889 kilowatt per hour. So this is the required energy to electrical energy to keep temperature of the air constant during this process. And to convert to kilowatt hour, we know that 1 kilowatt hour is 3600 kilojoules. So simply we can convert to the kilowatt hour. And even the temperature, here we assume that the temperature at the exit of the control volume is constant, 400. Even if it was not constant, we could do this simplification, do this assumption to select TE or to calculate TE as an average temperature for the exit of our control volume equal to T2 plus T1 equal to divided by 2 as our TE or temperature at the exit of our control volume. Then we could go through all of these steps to find this WEE. Here T is remain constant. Even it was not constant and it changed a little or it changed actually, we could use this equation T2 plus T1 divided by 2 as TE. Then we could do this calculation by this TE. By this we reach end of this chapter. Just I briefly summarize what I have told you in this chapter. We started with conservation of mass concept. We discussed about mass and volume flow rates. Then I introduced, or actually in global classroom, we have learned about the mass balance for steady flow process. And you learned how to write mass balance for incompressible flow, and we have seen examples for that as well. Then we discuss about flow work and energy after flowing flow. Then it was introduced the energy analysis of steady flow systems, and also I introduced different devices which we have steady flow for them, and we have calculated the energy balance and the mass balance for those devices, and we have seen different examples for those devices as well. And finally, we went through the energy analysis of unsteady flow process, and also we have seen different examples for this kind of process. Thank you very much for watching the video lecture.